Hello, fellow DefCampers. I'm Dragos, and today I'll be presenting an interesting research topic I've been exploring recently called securing networks using SDN and machine learning. Well, let's see how many of you are familiar with the concept of SDN. Raise your hand if you've used or implemented an SDN controller before. Okay, not a lot, I would say. So SDN is basically a different concept of thinking when you're routing traffic through the network. Instead of every network forwarding element taking its own decision of where to route traffic, you basically have a central controller deciding for each element where it should route the traffic. Well, you might be thinking that in that case, the controller needs to see part of the traffic and it will become a bottleneck. But that's not really so because, for example, when a switch first receives the first packet from for example, a TCP connection, it will only send that packet to the controller. The controller will look at it and decide where to forward it. And all of the other packets on that connection or flow will be sent to via the same path. So that's the big difference between SDN and the normal way of routing traffic. In the normal way, each routing element would have its own decision. Okay, do we have? Okay, so we're still waiting 5 minutes for everything to boot up. How many of you are familiar with machine learning? Okay, a few more. So to give you an introduction, machine learning basically means that you're trying to derive a model that you can then use to classify new examples or new stuff that you're looking at, new data. In the case of traffic flows, we're trying to classify flow types. For example, we want to say based on some features, a feature set, that this traffic flow is of type HTTP and that traffic flow is of type DNS, or maybe go even deeper. Let's say this traffic flow is for Facebook and this traffic flow is for Twitter. So based on some observable properties of that traffic flow, we can derive a model that we can use to classify it. Now, before we begin our presentation, let me give you a bit of background about myself. Well, I'm a software engineer / security worker, researcher working at Ixia in the application threat intelligence team. We basically do reverse engineering and emulation of network protocols and network attacks. So basically, our clients use our product to validate their network security and their network security devices, to be more specifically. And on the side, I'm also doing a PhD on software-enabled adaptive network traffic management. Well, that's the academic name for it. The short version is I'm trying to combine SDN with machine learning so we can create an adaptive network. To give you a short introduction about the problem we'll be exploring today, we know that traditional signature-based IPS-IDS approaches won't scale as the network becomes complex. So if you think about new device types that are appearing in the network with the IoT revolution and the M2M revolution, and each device type having different network layer protocols, different application protocols communicating with, and different application altogether installed on the same node. You can see that writing signatures to detect attacks for those applications is really not scalable. Even if you add a lot of work power to that, you won't scale sufficiently, and you won't be able to defend your network as effectively. So the solution I'm proposing is an adaptive way of defending the network. I'm basically trying to combine SDN, or let's say the flexibility of controlling your network via a centralized logic controller that takes the decision where to forward the traffic, with machine learning for getting data or let's say data on which you can take actions out of the network. So what this allows us to do, basically, I've outlined 3 scenarios in my talk today, is first of all, anomaly detection, botnet detection, and honeypot rerouting. Basically, as you'll see, both botnet detection and honeypot rerouting rely on anomaly detection. And we will talk about them later. Okay, so to give you an overview of what we're trying to do and how we're trying to derive the data from the network, we need to first understand what is a traffic flow. So if you think about it, you can resemble a traffic flow with a TCP connection or an UDP stream. And it's basically identified by 5 things: the source IP, destination IP, source port, destination port, and the transport protocol. In our case, TCP or UDP. So based on that, we're trying to classify traffic flows. We're trying to assign them a label so that we know that it's traffic of a certain type. But we're not doing that using deep packet inspection. Okay, we're doing that using observable properties of the traffic flow. For example, the packet sizes, different statistical measures of those packet sizes, such as the maximum, minimum, the mean, the flow time, for example, how many milliseconds it takes to complete that traffic flow or that traffic communication, and of course the interpacket delay time, how spread out in time are those packets. So based on those features, using supervised learning, in which for each traffic flow in our training data, we have a label associated with it, we can train a model. And when we introduce that model into a new network, it will basically detect with more or less high accuracy the type of that traffic flow. Okay, so having the type, we can send it to the SDN controller. And it can make decisions of where to route your traffic or what to do with it based on the flow type. If, for example, we don't have a model that matches that flow type, we can consider it as suspicious and an anomaly. And it might be or it might not be an attack. It might just be a new flow we haven't seen in the network before. So in order to distinguish that, we can run it through an unsupervised learning algorithm. An unsupervised learning algorithm, as opposed to a supervised one, in an unsupervised learning algorithm, actually, you don't have any labels for your training data. So the best it will do is basically cluster your data into different groups. So all of the HTTP flows, for example, or all of the specific HTTP flows will go into one group, and the other, for example, SMTP into another group dynamically. So based on unsupervised learning, we can deduce new flow types. And if we have sufficient flows of them, we can also train a supervised model for that flow type. In case a flow isn't really seen, it's just seen only a few times in the network, then we might call that an anomaly and mark it as suspicious, and also mark, using the SDN controller, the host that initiated it as suspicious as well. Okay, the third thing we can do after we have types associated with each flow is look for flow grouping, which flows go together in the network. For example, if you're looking at the YouTube page, you'll first have a DNS flow for obtaining the address of the YouTube server. Then you have an HTTP flow, and finally, when the user clicks the play button, you'll have a video flow. So having information about this group of free flows is important to the SDN controller, because, for example, if you know that the user is going to play the video, you can basically use the SDN controller to provision a path in the network in advance and optimize that traffic. Okay, based on these three information types, the SDN controller then programs your network devices with rules to where and when to route the traffic that's coming in. How do we integrate this information into an SDN controller? Well, most modern SDN controllers are basically event handlers, meaning that they receive events from the network. For example, a new traffic flow being initiated on a switch, and take decisions on those events and install rules in the network forwarding elements. So you have stream events coming into the controller, and those streams are transformed into forwarding rules. So in our case, integrating the machine learning information is quite simple. We could basically structure flow classification as events. For example, if on my forwarding element, I've measured the packet size and other features associated with other observable features associated with the flows, and I have the models already trained and evaluated those features against the models, then I can basically emit a flow match event if that particular flow matches the model, or a no flow match event if it doesn't match any model installed on the forwarding element. Okay, the same thing goes for the unsupervised and flow grouping part. For unsupervised learning, you can basically do it offline out of the network. And when let's say the clustering algorithm is complete and you found new flow types, then you can emit an event from that algorithm that tells the SDN controller you have new flow types and new models associated with those flow types. The same thing goes for flow grouping. So I've said we can enable three security scenarios. Now, the first one is, of course, anomaly detection. By using machine learning, you can basically have a baseline of your network. You can know which flows are typically seen in your network, and you can detect anomalies based on that when new flows that aren't really, let's say, aren't really in a high number in your network come in and okay. So the basic idea behind network anomaly detection is to continue to train and refine our supervised model for the traffic flows in our network. And when a flow doesn't match any model, we flag it as suspicious. We add it to the queue to the clustering algorithm, and then we run clustering with side information. Side information meaning source ports, destination ports, and other layer 2 free addressing information to see if there are other flows similar to it. If that particular flow is in a separate cluster and we don't have really any flows similar to it, then it's likely an anomaly. If not, and we find, for example, a cluster that's similar to it, and in that cluster we already have flows from another train supervised model, then we refine that model with the new flow type. Okay, now botnet detection. So a bot is typically a group of hosts that communicate periodically with a command and control server and receive commands from it that then get executed. Example of commands received from the CNC server are those for performing distributed denial of service, scanning the local network, sending spam, and other stuff. So in this case, the communication flow with the command and control server would be basically flagged as an anomaly because we haven't seen it in our network so far. And the other communication flows that are initiated after the command is received, for example, for scanning the network, would be classified as a related group of flows. So if we have this combination, anomaly plus group of flows, of related flows originating from the same host afterwards, then there's a high probability that we have a bot in our network. The first scenario is honeypot traffic rerouting. As before, if a flow doesn't match any supervised model we have trained for our network, Then we mark the host which initiated it as suspicious and store the flow five tuple associated with it. So the five tuple is basically the source IP, destination IP, source port, destination port, and transport protocol. The next time that host that initiated the suspicious flow is trying to communicate, we instruct the SDN controller to reroute that flow through a honeypot. And having information about where it's trying to connect and what port and other characteristics of the flow, we can basically program our honeypot to receive the exact flow, to emulate the exact scenario our attacker is trying to do. So we can trick him into actually believing he's hacking a real machine and gain information from it. So to give you an overview of how our system architecture would look like when deployed in a real network, on the right, we have the network forwarding elements. They're basically SDN switches that have been enhanced to also have a traffic and machine learning traffic classifier associated with them. We install supervised classification models on them for classifying traffic type. And we also install forwarding rules, of course, because it's SDN, and we receive flow classification events from them in the SDN controller. The SDN network controller in the middle, as I've said, is a logical controller, meaning that you can have multiple instances, multiple, let's say, VMs in our case, running the control logic, and each VM can be partitioned to only handle some of the network forwarding elements. Only handle control for that. All VMs communicate or let's say maintain the network state via common distributed data store. And for the unsupervised part, this network controller also communicates with a Hadoop cluster that's used for running the unsupervised learning algorithms. In this case, it will send the traffic flow features it's found in the network that haven't been seen before, and the network controller will send these features, and it will receive back from the Hadoop cluster after the algorithm has completed running new classifier models it can install on the network forwarding elements and flow groups. So we basically evaluated the first part of our proposed system, meaning the supervised learning part, where we have already pre-trained our models, our flow classification models. This is how our experimental testbed looks like. We basically have a mininet VM simulating an SDN topology with 4 OpenVC switches. And in that VM, we also have the diffuse machine learning classifier. Diffuse is actually quite cool. It's a kernel module developed on top of the IP firewall. It basically sits in the mininet VM and monitors all of the traffic flows that come in and computes features for them and tries to match them against the model it has installed in it. Okay, all of the 4 switches are controlled by a machine learning enhanced SDN controller, and for traffic generation, we're using the XCR breaking point application traffic emulator. And it's connected to a port in every one of those switches. Now, for testing and results, we've used the traffic emulator to simulate 3 types of networks. One is enterprise, and we can see what type of traffic flows where we typically see in an enterprise on the screen. The other one is a small business, and the third one is an ISP network. So the breaking point traffic emulator can simulate all of the protocols that would typically be present in these types of networks. So for enterprise, you can see we have HTTP, of course, SMTP, DC, RPC, SIP, and other types of protocols, SSH, you would find in an enterprise. With each protocol, you can associate how much bandwidth you would like it to consume, or how many flows would you like it to initiate during a test. So we can see that most of our bandwidth is hogged by the video flows, the HTTP video, the first flow. Okay, so we use these free application profiles to simulate, let's say, as close as possible to a real network. And that was for the legitimate traffic. For the malicious traffic, we also introduced several network attacks. This is basically an attack list with 607 critical strikes, meaning strikes that have a CVSS score of 10. That's the maximum. And besides these network attacks, we also introduced botnet traffic. This is typically the command and control traffic. We had in the breaking point product 1,646 different botnets emulated, and most of them were HTTP based. So how did we proceed to evaluate the system? Well, for training data, we generated 256 different communication streams for each flow type in the application profile. The breaking point product basically can randomize certain parts of the flow so you don't get the same payloads every time, and you get a variation. So you can use that variation as training data as a lot of pre-labeled examples for your model. After that, we proceeded to train the classification model for diffuse for each flow type through the Weka machine learning framework. And after we trained and installed our models into diffuse, we measured the classification accuracy afterwards after running the same application profile through the network with and without the attack and botnet traffic. Without that type of traffic, we obtained an accuracy of 82% for the enterprise case, 87% for the small office, and of course 79% for the ISP case. Sandvine is actually the name of the application profile we used. Sandvine basically publishes reports on the typical traffic you'd see in an ISP network. Now, with attack and botnet traffic, of course, the probability for false positives and false negatives and basically errors increases pretty much. So we have the accuracy is reduced quite a bit. But given these figures, they're, let's say, a bit lower than you would expect from a typical IPS or IDS, but in any case, they're okay. In machine learning, everything above, let's say, 60% is okay. So we can, as we add more training example, we can improve these numbers. Now, with regards to classification time, of course, I've said that for each traffic flow, we need to measure and compute statistics, such as the minimum, mean, maximum, and standard deviation and sum of the packet sizes. Let's say the packet sizes themselves for the first n packets, and the, let's say, communication pattern, who is sending which packet and in what order. So for this type of scenario, we were interested in the classification time, meaning how many packets do we have to inspect before we can reach a conclusion about the flow type. And we basically did the experiment per flow type. So for example, for flows that are based on simple fixed size protocols, you need a lot less packets, while for other flows that, for example, the HTTP case is text-based or FTP, you need a lot more packets to inspect before you can come to the conclusion that that flow is of a certain type using these features over here. Okay, now a bit about the resource usage overhead. So as I said, in our experimental setup, we had one mainnet VM with the diffuse machine learning classifier installed, simulating a topology of 4 switches, and a learning switch SDN controller running in the same machine. In this case, we used the breaking point traffic emulator to basically emulate around 100,000 concurrent flows. And the throughput was around 25, 30,000 packets per second. Okay. We can see that the CPU usage when enabling diffuse, so we basically did 2 experiments, one with diffuse disabled and one with diffuse enabled. And the CPU usage overhead with diffuse is around 17% because for each traffic flow, it will compute the statistics and try to match it against the supervised model. And the memory usage overhead was 13% because the memory usage basically comes from that state information it's associating with each traffic flow when it tries to match it and compute statistics on it. Okay, some things I would like you to take away from this talk. We can do machine learning, flow classification, and SDN in order to make the network more adaptive. We've seen how we can easily integrate that and what types of scenarios we can support. And we can also extract quite a bit of information using machine learning from the network. The first type of information is flow type classification, of course. Next, we can use the unsupervised learning to derive new flow type classifiers. And of course, we can use flow grouping to see which communication flows come together in a network or are typically seen together. This enables us to, from a security standpoint, enables us to do anomaly detection, botnet detection, and honeypot rerouting. And of course, after seeing the overhead that diffuse introduces, we can also conclude that machine learning classification overhead is manageable. Okay, and we have a lot planning to. We have a lot of plans following this talk. We basically explored only the supervised part, so we're now ramping up on the unsupervised learning and flow grouping. And we also would like to see the system deployed in a real network so we can see the exact, let's say, behavior it has and whether it can learn everything in that network. So if you guys have any questions.
Would this system help against DDoS attack? For example, can you classify something like that? You spoke about botnets, but
Yeah.
can you be more specific in this direction?
Okay, so a DDoS attack, you'd basically have the same flow type coming in from different areas outside of your network. In that case, I think the first flow would be classified as an anomaly. And for the other flows, you can basically program the SDN controller so that when it detects flows from that type to blacklist the addresses that are sending those flows.
Other questions? No? Then thank you so much for your presentation.